Welcome to the Deep Dive. Today, we're going inside your computer. We're exploring something you might not think about much, but honestly, without it, your high-powered graphics card, your super-fast SSD, they just wouldn't work the same way.
Yeah.
We're talking about PCI Express or PCIe.
Yeah, the highway inside the machine.
Exactly. Think of it like the ultimate set of super-fast connections inside your PC. Now, you, our listener, pointed us towards some really great sources on this.
Yeah.
So our mission today is to understand how PCIe got to where it is, and maybe more importantly, why it matters. We'll try not to get too bogged down in, the super technical jargon.
We'll focus on the why.
Yeah, the why behind all this speed, because you see PCIe connecting a huge range of components. We mentioned graphics cards, obviously, but also network cards, sound cards, those incredibly quick NVMe solid-state drives, all sorts of stuff.
It really is foundational tech for modern computing. It underpins so much.
Okay, so let's unpack this. Where do we start? The beginning.
Let's start at the beginning. To really get PCIe today, you kind of have to look back at what came before it.
Okay.
Before PCIe, the main standard inside most computers was the original PCI bus. Remember that? Intel introduced it way back in 1992.
92, wow.
Yeah. And it was a parallel bus. It was actually a pretty big leap forward from even older things like ISA or ISA.
Oh, yeah, those were ancient.
PCI gave us faster speeds. It had this clever feature called bus mastering. It lets devices talk directly to memory.
Right.
And plug and play, which made adding hardware way easier.
Oh, I remember the bad old days of IRQ conflicts. PCI definitely helped there. But, as things got faster, that parallel design, it started hitting a wall, didn't it?
It really did. It became a bottleneck. Think of it like a wide road, but everyone's trying to get through the same single toll booth.
Yeah, okay.
To get more speed out of PCI and its successor PCI-X, engineers kept trying to increase the clock speeds. But with a parallel bus, you've got all these data signals traveling side by side. Keeping them all perfectly synchronized gets really hard, really fast.
Like herding cats, but with electrons.
Kind of. You get issues like signal skew, where different bits arrive at slightly different times, causes errors, limits the speed. You just couldn't reliably push it much further.
So that bottleneck, that's what led to the big shift around, 2003, 2004?
Exactly. That's when PCIe was born. And it wasn't just like a small tweak. It was a radical change.
How so?
They moved from that shared parallel approach to a high-speed serial point-to-point system.
Okay, serial instead of parallel, point-to-point. What does that mean exactly?
It means instead of everyone sharing the same bus, each PCI device gets its own dedicated connection, its own link directly to the system controller or maybe a switch.
Like individual tunnels instead of one big road.
Precisely. And the link is made up of one or more lanes. Think of a lane as a two-way street for data. It's full duplex.
Full duplex meaning data goes both ways at the same time.
Yep. No waiting for traffic coming the other way. Each lane is its own independent data pipe, sending and receiving simultaneously.
Okay, so these lanes are key. We always see specs mentioning by 1, by 4, by 8, by 16 slots. That's just the number of lanes for that connection.
That's exactly it. More lanes, more potential bandwidth. And by 16 slot has 16 of these lanes bundled together.
Got it. 16 times the capacity even by 1, basically.
Assuming the same PCIe generation, yes. And this whole system, the standards, the rules, that's managed by the PCI Special Interest Group, the PCI SIG.
Right, the standards body.
Yeah, it's a huge industry consortium. Over 1,000 companies, Intel, AMD, NVIDIA, all the big names are members. They make sure everything works together.
And the clever part.
The really clever part was, even with this massive change underneath going from parallel to serial, they designed PCIe to be software compatible with the old PCI way of doing things.
Oh, really? So operating systems didn't need a total rewrite?
Nope. Drivers, OS. They could largely interact with PCIe devices using the same models they used for PCI. Made the transition much, much smoother.
That's smart engineering. Okay, so we've gone from parallel PCI to serial PCIe. But the story doesn't stop there. PCIe keeps evolving, right? These generations.
Constantly. That's one of its biggest strengths. Every few years, a new generation comes along, and the basic rule of thumb is it doubles the bandwidth.
Doubles it every time.
Pretty much doubles the data rate per lane, and crucially, they've always maintained backward compatibility.
Right, that's huge. So a new card works in an old slot and vice versa.
Yes, though they'll run at the speed of the slower component, obviously, but it means you don't have to upgrade everything at once.
Makes sense. Let's walk through these generations then. Where did it start? PCIe 1.0.
Yep. PCI 1.0, and its minor update 1.1 kicked off around 2003-2005. The raw speed, what they call the data rate, was 2.5 gigatransfers per second, or GTs per lane.
Gigatransfers.
Okay, but there's a catch. To send data reliably, they use an encoding scheme. Back then, it was 8B, 10B encoding.
8B10, what does that mean?
It means for every 8 bits of actual data, they send 10 bits over the wire. The extra bits help with things like clock recovery and error detection, but it adds overhead.
So you lose some of that raw speed. How much?
About 20% overhead. So that 2.5 GTs translated to an effective bandwidth of around 250 megabytes per second per lane.
Okay, 250 megabytes per lane. For a typical by 16 graphics card slot, that's
16 times 250, so about 4 gigabytes per second total.
right. Then came PCIe 2.0.
Around 2007, doubled the raw rate to 5.0 GTs per lane. Still use that same 8B, 10B encoding, though.
So double the raw speed, same overhead. Means double the effective speed.
Exactly, about 500 megabytes per lane or 8 gigabytes for an by 16 slot. Simple doubling.
Okay, straightforward enough. What about PCIe 3.0? That seemed to stick around for a long time.
It did. Came out in 2010. The raw speed went up to 8.0 GTs per lane. Not quite double, but the big change was the encoding.
They changed the encoding.
Yeah, they moved to a much more efficient 128B, 130B scheme.
128B, 130B, less overhead.
Much less. Only about 1.5% overhead compared to 20%. So even though the raw speed didn't quite double, the effective bandwidth per lane jumped to nearly 1 gigabyte per second.
Wow, okay, so almost double the usable speed again.
Pretty much, around 0.985 gigabytes per lane, which is about 15.75 gigabytes for an by 16 slot. That efficiency boost was huge, made PCIe 3.0 very capable for years.
And they moved other things too, signal integrity.
Yeah, as speeds climb, keeping the signal clean is vital. They introduced better equalization techniques to compensate for signal loss.
Makes sense. So after the long reign of 3.0, we got PCI 4.0.
Right, in 2017, back to doubling the raw rate. 16.0 GTs per lane.
And kept the efficient encoding.
Kept the 128B, 130B encoding, so effective bandwidth per lane doubled again to just under 2 gigabytes.
Giving us around 31.5 gigabytes for an by 16 slot?
Correct. PCI 4.0 also focused more on flexibility, lower power, and things like Oculink for external cable.
External PCIe. Interesting. And then just 2 years later, PCIe 5.0. That seemed quick.
It was quick. 2019, doubled again. 32.0 GTs raw rate per lane, same 128B, 130B encoding.
So we're looking at nearly 4 gigabytes per lane.
Just about. Roughly 3.94 gigabytes per lane, or a massive 63 gigabytes total for by 16.
63 gigabytes per second. What needed that much speed so quickly after 4.0?
The big drivers were data centers, AI, and machine learning workloads, and really high-speed networking. Those areas were just exploding.
Ah, the AI boom.
Exactly. We started seeing platforms with PCIe 5.0 around 2022, and the latest NVMe SSDs started taking advantage of it.
Which brings us to the current cutting edge, PCIe 6.0 from 2022. Another doubling.
Doubled the raw rate again, yes, to 64.0 GTs per lane.
Yeah.
But this time, how they achieved it changed quite a bit.
Oh, not just faster clocks and the same encoding.
Nope. They introduced a new signaling method called PAM4.
PAM4. Okay, break that down.
Okay, so traditional signaling called NRZ uses 2 voltage levels, basically 0 or 1. PAM4 uses 4 distinct voltage levels.
4 levels.
Right, which means each signal transition can represent 2 bits of data instead of just 1. So you can double the data rate without doubling the frequency, which helps manage signal integrity issues.
Clever, but there's a downside.
Yeah, those 4 levels are closer together, making the signal more susceptible to noise and errors. So PCIe 6.0 also had to introduce forward error correction, or FEC.
FEC fixes errors on the fly.
Essentially, yes. It adds some redundant data that allows the receiver to detect and correct a certain number of bit errors without needing a retransmission. They also use something called FLIT mode encoding, which is different from 128B, 130B.
So new signaling, error correction. What's the final usable speed?
After accounting for PAM4, FLIT, and FEC overhead, the effective bandwidth is around 7.56 gigahertz per lane.
So nearly a double 5.0 again. That's 121 gigas for by 16.
Roughly, yeah, absolutely staggering speeds. This is really aimed at the high-end enterprise, AI, high-performance computing markets. We're just starting to see silicon for this now, maybe wider availability 2024, 2025.
Wow, that progression is just relentless. Having that table summary really helps visualize it.
Yeah.
Okay, so speed is obviously key, but you mentioned backward compatibility earlier. That seems like a massive pillar of PCI's success.
Absolutely crucial. It's probably the most important factor for its longevity and widespread adoption, besides the speed increases.
Why so important?
Well, imagine if every time a new PCIe generation came out, you had to replace your motherboard and all your expansion cards simultaneously. It would be incredibly expensive and disruptive.
Yeah, nobody would upgrade.
Exactly. Backward compatibility means you can upgrade incrementally. Got an older motherboard but want a new graphics card? It'll work, just maybe at PCI 3.0 or 4.0 speeds instead of 5.0.
And the other way around, an old card and a new motherboard.
Works too. It'll just run at the speed the older card supports. This compatibility applies to the physical slot. A new card fits in an old slot and the software interface.
And you can put smaller cards in bigger slots, right?
Yeah.
Like a buy one network card and a buy 16 slot.
Yep, absolutely. The system just negotiates to use the number of lanes the card actually has. It protects user investments, simplifies system building for manufacturers. It's just a win-win.
Definitely a cornerstone. Okay, another thing you touched on was power management. Early high-performance stuff could be pretty power-hungry. How has PCIe tackled efficiency, especially for laptops and stuff?
That's another critical evolution. While, yeah, high-end server cards can draw a lot of power, the PCIe standard itself has become incredibly sophisticated at saving power when possible. This was vital for getting PCIe into mobile devices.
How does it work? Different power states.
Exactly. They define various L states. L0 is fully active, maximum performance, maximum power. Then you have progressively deeper sleep states, L1, L2, L3, where parts of the link are powered down to save energy when there's no data to transfer.
Okay, deeper sleep saves more power, but maybe takes longer to wake up.
Generally, yes. But the real breakthrough for mobile came after PCIe 3.0 with the introduction of L1 substates, specifically L1.1 and L1.2.
L1 substates, what's special about them?
They allow the really power-hungry parts, the high-speed transmitters and receivers, to be almost completely shut off during idle periods, but they maintain a very low-power side-channel communication link.
So they can wake up quickly when needed.
Much quicker than waking from a full L2 or L3 state, but they save a ton of power compared to just L0 or the basic L1 state. We're talking potentially hundreds of milliwatts down to just a few milliwatts.
Wow, that's a huge difference for a battery.
Massive. It strikes that balance, save significant power, but remain responsive. Things like latency tolerance reporting, LTR, also help, where devices tell the system how much delay they can handle, allowing for smarter power decisions.
And even PCIe 6.0 has new power tricks.
Yeah, they added an L0P state for even finer grain savings. It's clear these power management features, especially those L1 substates, were absolutely essential for PCIe to become dominant in laptops and other mobile gear.
Fascinating. It's not just about going faster, but doing it efficiently. Okay, let's talk drivers. What applications have pushed this need for speed? You mentioned graphics cards, the first big one.
Yeah, initially, GPUs were outgrowing the old AGP bus.
Yeah.
PCIe by 16 gave them the dedicated bandwidth they desperately needed. That was the first major driver.
And then, what came next?
High-speed storage, specifically NVMe SSDs.
Ah, the move away from SATA.
Exactly. SATA was designed for spinning hard drives that copped out around 600 millibics. NVMe SSDs, using flash memory over PCIe, could go way faster.
So fast they started hitting the limits of early PCIe.
Pretty quickly, yeah. A good NVMe drive on a PCIe 3.0 by 4 link, that's a common setup for M2 SSDs, could hit around 3.5, maybe 4 gigabits. They saturated that link.
So that puts the need for PCIe 4.0.
Absolutely. PCIe 4.0 by 4 doubles that potential to around 8 gigabits. And now with PCIe 5.0 by 4, we're seeing drives pushing past 10, even towards 14 gigabits. Storage became a huge driver for PCIe bandwidth.
Okay, graphics then storage. What about more recently? The jump to 5.0 and 6.0 seemed really fast.
That acceleration is almost entirely down to AI, machine learning, high-performance computing, HPC, and the massive data movements within data centers supporting all of that.
It's the data center and AI now.
Overwhelmingly, yes. Training huge AI models, running complex simulations. It requires insane amounts of data to be moved constantly between CPUs, GPUs, specialized AI accelerators, high-speed networking cards, all connected via PCIe.
So while gamers benefit, they aren't necessarily the main reason for PCIe 6.0 speeds.
That seems to be the case. For many games, the difference between a high-end GPU running on PCIe 4.0 versus 5.0 is often pretty small, sometimes negligible in terms of actual frame rates. The GPUs themselves aren't always bottlenecked by the bus in typical gaming scenarios.
Interesting. So the cutting edge of PCIe is really being forged in the fires of AI and HTC right now.
It strongly suggests that, yeah, the PCI SIG explicitly calls out these markets as the primary drivers for 5.0, 6.0, and the upcoming 7.0.
Okay, let's dig into that NVMe connection a bit more. You said it uses PCIe. How does that work?
So NVMe stands for Non-Volatile Memory Express. It's not the physical connection that's PCIe, it's the protocol, the language spoken over that connection.
A language optimized for flash memory.
Exactly. Old protocols like SATA with the HCI command set were built assuming slow, spinning disks with high latency. NVMe was designed from the ground up for the low latency and high parallelism of flash memory communicating over a fast bus like PCIe.
What are the main advantages over, say, SATA GICF?
Lower latency is a big one because it cuts out layers of the old storage stack and talks more directly over PCIe. Higher transfer rates, obviously, thanks to using PCIe lanes. But maybe the biggest architectural win is parallelism.
Parallelism, how so?
HCI basically had one command queue, holding up to 32 commands. Think of it as one tiny instruction book. NVMe supports up to 64,000 queues, and each of those queues can hold up to 64,000 commands.
Whoa. 64,000 times 64,000.
Yeah, it's a theoretical maximum, but it allows for massively parallel operations. Instead of waiting for one command to finish, the drive can be working on thousands simultaneously. This leads to much, much higher IOPS input-output operations per second.
Which is critical for servers and heavy workloads.
Absolutely. And like we said, the performance scales directly with PCIe. PCIe 3.0 by 4 gets you maybe 3.54 gigabits sequential reads. PCIe 4.0 by 4 pushes over 7 gigabits. PCIe 5.0 by 4 is doing 10, 12, 14 gibbles now.
They really grew up together, PCIe and NVMe.
It's a perfect example of synergy. PCIe provided the fast pipe, NVMe provided the efficient protocol to fill it with data from flash memory, and NVMe itself keeps evolving too, adding features.
Makes sense.
Yep.
Okay, now another acronym you mentioned, CXL, Compute Express Link, also related to PCIe.
Very much so. CXL is newer, still emerging, but it's built on top of the PCIe physical layer.
So it uses the same wires, the same electrical signals as PCIe.
Fundamentally, yes. When a CXL device connects, it first negotiates using standard PCI protocols, but then it can switch to using specialized CXL protocols over that same physical link.
Okay, so it's like running a different kind of traffic over the PCIe highway. What kind of traffic? What's CXL for?
CXL is primarily focused on improving memory access and enabling new memory architectures, especially in servers and data centers.
Memory. Interesting.
It defines three main subprotocols. CXL.io is basically just PCIe for standard I/O functions. Then there's CXL.cache.
CXL.cache.
Yeah. This allows devices like accelerators or smart NICs to maintain cache coherency with the CPU's memory. It means everyone agrees on what the current correct data is in memory, which is crucial for shared memory systems.
Okay, keeps everyone on the same page data-wise.
Exactly. And the third one is CXL.m. This lets the CPU directly access memory that's attached to a CXL device.
So you could have memory physically located on an expansion card, and the CPU treats it almost like main system RAM.
That's the idea. It opens up possibilities for memory expansion, just adding CXL memory cards and memory pooling or sharing between processors and accelerators in ways that weren't really efficient before.
Sounds like it addresses some big bottlenecks in server design.
That's the goal. CXL aims to tackle memory bandwidth limits, reduce the latency for accelerators needing access to large datasets in memory, and allow for more flexible and efficient use of memory resources overall.
Are there different types of CXL devices?
Yep. Three main types are defined. Type 1 are accelerators, maybe like a basic GPU or FPGA, that don't have their own memory but use CXL.io and CXL.cache to work with the CPU's memory coherently.
Yeah.
Type 2 devices are more advanced accelerators with their own attached memory. They can use all three protocols, CXL.io, .cache, and .mem, allowing the CPU to access their memory and them to access the CPU's memory coherently.
So they can share memory pools.
Right. And Type 3 devices are basically just memory expansion modules.
Yep.
They use CXL.io for management and CXL.mem to provide additional memory capacity to the CPU over the PCIe bus.
Very cool. And CXL versions are tied to PCI versions.
They are. CXL 1.1 and 2.0 were designed to run over the PCIe 5.0 physical layer. CXL 3.0 and 3.1 leverage the faster PCIe 6.x physical layer. It shows how PCIe is becoming this foundational fabric that new specialized protocols can build upon. It's not just for peripherals anymore.
It's becoming a more universal interconnect. Fascinating stuff. So where does PCIe go from here? We've hit 6.0. What's next?
PCIe 7.0 is already well underway. The PCI SIG is actively developing it, aiming for a final specification release sometime in 2025.
And the goal? Let me guess. Double the speed again.
You guessed it. Double the raw data rate per lane to 128 GTs.
128 gigatransfers per second per lane.
Which, for a full by 16 slot, would mean a theoretical bidirectional bandwidth of 512 gigabytes per second.
Half a terabyte per second. That's just mind-boggling. How are they achieving that? Still PAM4.
The plan is to continue using PAM4 signaling, along with FLIT mode encoding and forward error correction. They're essentially refining and pushing that technology further.
So focusing on optimizing PAM4 rather than inventing something entirely new this time.
It seems so. The main goals are reliable signaling at that speed, improving power efficiency, keeping latency low, maintaining high reliability, and of course, preserving that all-important backward compatibility.
And who needs half a terabyte per second? Still AI and HPC.
Primarily, yes. Think 800 gigabit Ethernet and beyond, next-gen AML clusters, even more demanding HPC, maybe quantum computing interconnects, plus hyperscale data centers, specialized military aerospace applications. That's the target.
When might we see actual hardware?
If the spec is finalized in 2025, you'd typically expect the first hardware products implementing it maybe around 2027 or 2028. It takes time to design and validate silicon at these speeds.
It sounds like they're really pushing copper wires to their absolute physical limits now. Can copper keep up indefinitely?
That is the big question hanging over the future. Signal degradation, crosstalk, distance limitations. These all get exponentially harder as you increase frequency and data rates on copper.
So what's the alternative?
The PCI is openly acknowledging this and is actively exploring optical interconnects for future PCIe generations beyond 7.0.
Optical, like fiber optics inside the computer.
Potentially, yes. Or at least for connecting modules or chassis over slightly longer distances within a rack or system. Optical fibers have much lower signal loss, they're immune to electromagnetic interference, and can carry vastly more data.
We already use optical for networking between computers.
Exactly, and we're starting to see prototypes. Kioxia showed off optical PCIe 5.0 SSDs that could connect over much longer distances than copper allows.
Wow. What would shifting to optical mean? New connectors?
Almost certainly. It would be a huge shift. New connectors, new onboard components, optical transceivers, potentially a blurring of lines between internal I/O and networking. It could enable radically different, more distributed system architectures.
But probably more complex and expensive initially.
Likely, yes. There are challenges around cost, power consumption of the optical components, thermal management, and just the engineering effort involved. But at some point, the limitations of copper might make the switch necessary to keep scaling performance.
It's amazing to track this journey. From that parallel PCI bus in '92.
Right, struggling to get past a few hundred megabytes per second.
To PCIe 6.0, hitting over 120 gigabytes per second today. And 7.0 aiming for half a terabyte per second.
And now seriously considering leaving copper behind for light itself, it's been an incredible evolution.
Yeah, summarizing it, you've got this relentless doubling of speed, generation after generation. You've got that crucial backward compatibility keeping things usable.
The power management innovations that let it go mobile.
The driving forces shifting from graphics to storage and now heavily into AI and the data center.
And then these extensions like NVMe completely changing storage and CXL rethinking memory access, all built on that PCIe foundation.
It really is easy to overlook, but PCIe is just so fundamental to how our computers work today. It enables almost everything high speed that we do.
Absolutely. It's the unsung hero inside the box.
So a final thought for you, our listener. Consider this. As PCIe continues to evolve, especially if it makes that leap towards optical interconnects, how might that fundamentally change the computers of the future?
Right. Think about what happens when the physical distance limitations of copper inside a server rack, or even inside a single complex machine, start to dissolve.
Could we see systems where CPUs, memory, GPUs, storage are much more physically distributed but connected by ultra-fast optical PCIe links? What new kinds of devices or applications could that unlock?
What happens when the difference between talking to local memory and memory across the rack becomes much smaller? It's definitely something fascinating to think about.